Alright, so in the last demonstration I showed how to use the Morlet Wavelet Decomposition function, or the MWD function, to create Morlet wavelets in a few different ways. The MWD function, of course, is the standalone function, meaning that it does not require EEG lab to run. It will simply take an inputted EEG signal matrix and convolve that signal with as many Morlet wavelets as are defined. It will output the Morlet wavelets and some additional information, as well as the results of the convolution. In the last demonstration, though, we ignored the results of the convolution and instead just focused on the Morlet wavelets themselves. But in this demonstration, we're actually going to examine those results. So in this demonstration, I'm going to create a simulated EEG signal, and that's going to be made of three different components: a 12 Hz alpha component, a 16 Hz low beta component, and a noise component. This noise component is made of three subcomponents: just a random vector, a slow wave drift, and mains hum, or a 60 Hz line noise. All three of these components get summed together to create the mixed signal, or the simulated EEG signal. And I'm just going to run this section to plot what I've just described here. So below in red are the signal components that I created. This is the 12 Hz alpha component. It starts with 0 energy, it suddenly comes online, goes away, comes online again, and then over here at 3 seconds, it inverts its phase and increases in amplitude and then goes away again. And so the main characteristic features of this alpha component are its sudden energy shifts and the phase inverse. And the 16 Hz low beta component has a Hanning window applied to it, so it comes and goes rather smoothly. And then down here is the noise component. There's that slow wave drift there, the random noise, and there's a 60 Hz sinusoid in there. All three of these summed together make the mixed signal up here, and it's this mixed signal that we're going to convolve with different Morlet wavelets using the MWD function to try to extract these two target components, the alpha and the beta components. Just to start a little simpler though, I'm going to remove the low beta component for a moment. And so now this is flatlined and our mixed signal is much simpler now. It's just a noise component and an alpha component. Down here is where I convolve the signal. Here's where I call the MWD function. I've passed in the mixed signal and the sampling rate, and I'm going to define the wavelets that I want in a minute. Now, after using MWD to convolve a signal with different Morlet wavelets, the first three output arguments are the results of that convolution. And these are the output arguments that we discarded in the last demonstration, where we only focused on the DAT output argument, which contains the wavelets and information about those wavelets. So the first output argument is the bandpass signal. Remember, I described wavelet convolution as a bandpass filter. Well, this is the bandpass result, so it's a real signal with real oscillations. The time domain power and time domain phase are generally what people are interested in when they're using a Morlet wavelet decomposition, because a bandpass signal, of course, you can get by using a more traditional filter. Now, I don't actually plot the time domain power here. Instead, I take its square root to create the time domain amplitude, and that'll just make it easier to plot in a moment. But first, I'm going to ignore time domain amplitude and phase and only show the bandpass signal, since it'll be easier to compare the extracted component with the real component. So right now, I just want to extract this alpha component from the mixed signal. So I'm interested in a 12 Hz component, and so I'm going to use a 12 Hz Morlet wavelet. And just for starters, I'm going to define that wavelet to have a cycle count of 4. Now when I run this, it's going to convolve this 4-cycle 12 Hz Morlet wavelet with the mixed signal, and it's going to plot the bandpass signal next to the alpha component. And they're plotted next to each other for comparison. Again, the red being the true underlying component, and the blue being the estimation of that component taken from this mixed signal. And this is a pretty good output. They're very similar to each other. You are, though, getting some non-zero energy out here where the underlying component is 0, and that's primarily because of this noise component bleeding in. It also registers these sharp energy transitions relatively quickly, and that's because we had a pretty low cycle count. And we can register these quick transitions better by lowering the cycle count. So let's go down to 2 1/3, which is really as low as is recommended to go. Oh, and I didn't clear my figure, so there we go. And so now these transitions are registered a little more sharply. But I'm going to bump this back up to 4 for now, because it'll be easier to look at. Now also, I'm going to plot the time domain amplitude, and it'll look just like an envelope encompassing the estimated component. And then the time domain phase, which ranges from -pi to pi. And this is in terms of a cosine, meaning that all zero crossings are a positive peak in the oscillation. Now though, let's add the 16 Hz beta component back into the mix. And then with this added into the mixed signal, you'll see that the decomposition becomes worse. There we go. And what you see now is we have a lot more non-zero energy in the extract component where there is zero energy in the true component. And that's because it's picking up a lot of this 16 hertz energy down here. And so although our center frequency is 12 hertz, we have a half maximum width of 7 hertz. So a passband ranging from approximately 8.5 hertz to 15.5 hertz, which of course is going to retain a lot of the 16 hertz energy. Now, real quick, let's also try to extract the 16 hertz component. So I'm going to add a 16 hertz wavelet, both with 4 cycles. And you can see the results of this decomposition are very poor as well. And again, this is primarily because we have such a wide passband, or half maximum width in the frequency domain. So let's actually try to narrow that up. Let's say now instead of a 7 and 9 hertz half maximum width, let's define both of these to have a 1 hertz half maximum width. Very, very narrow. And now we're doing quite a lot better in certain respects, particularly in the case of the beta component. We've captured the smooth handing window that was applied to that 16 hertz component, but in the alpha component, now we're looking quite poor again. But rather than picking up energy from other frequencies, now what we're doing is we've actually lost all our temporal precision. So the sudden energy change in the alpha component has now been smoothed over. Rather than a boxcar shape that we would hope in the amplitude, we have a very smooth, approximately Gaussian shape. Also, this phase reversal was registered about 100 milliseconds early. So although this very narrow frequency band is good for the beta component, we really need to focus on a better time domain half maximum width in the alpha band. And that's simply because of the energy profile of that component. So let's try pushing the 12 hertz wavelet half maximum width up to 5 hertz. And that'll of course decrease our time domain half maximum width and hopefully capture those sudden energy changes. And now running this, we've regained our temporal precision, but it's been at the expense of a frequency precision. And so it's capturing some of that 16 hertz energy again. And our beta extracted component is doing very well. And so of course, in a real situation, you're always going to be playing back and forth with the time and frequency precision trade-off. And you're going to have to make those decisions based off what you expect the underlying components to look like and what really you're after. And that's always going to be context dependent, of course. And simulated signal exercises like this is going to help you determine what you'll need to capture different scenarios. So you can try coming into this demo script and adding new components and reshaping these components and playing around with different Morlet wavelets to try to extract them.